Hello everybody, this starts our official entry into real-world questions, specifically quadratics in the real world. It says the following graph represents the height of a diver. So if we look at our picture here, we have height in meters on the y-axis, time in seconds on the x-axis, and this is the path of the diver as he is diving into the water. Number 1 says, circle where the diver would hit the water or the ground. So when you look at this picture, at what point does it represent him hitting the water or the ground? Hopefully a diver would not be hitting the ground. That would be bad. So let's see. When I look at this graph, I see this is where he started and then made the dive. So right here, I'm going to circle there. That's where he hit the water. This would be finding so the question is, what are you finding on the graph? Well, I know that this is my y-axis, this is my x-axis, so this ordered pair right here would actually count as an x-intercept. So that would be as an ordered pair. From 0, 0, we go right 3.5, and then it's comma 0, because when I go right to 3.5, we are not going up or down at all. Looking at number 2, it says place an X where the diver reaches their highest point. So let's see, coming back here, let's see, where's that highest point? Where would you say the highest point is? Well, if I literally go by the height, and I look for the highest point on the graph, looks like it's right there. Reached his highest point. We call that finding the vertex. Vertex is the vocabulary word for the highest point on that graph. And now let's see if we can find that ordered pair. It's counting by 0.5, so this is, 0.25. 0.25, 0.5, 0.75, 1. So kind of like between 1 and, that would be 1.25. So maybe like 1.2, comma 30. .2, comma 30. And if we interpret what that means, actually both of those ordered pairs we've looked at, here, this first one, at 3.5 seconds, his height away from the water is at 0. So this one meant 3.5 seconds, 0 feet above water. He's literally at the water, 0 feet above it. So how would you interpret this second ordered pair? Give it a try and then we'll see if we match. X and Y. X represents time in seconds. So at 1.2 seconds, the diver has reached a height of 30 feet. And because this is the vertex, this is the maximum height. Because it's the vertex. Very good. Number 3 says, put a box where the diver would reach a height of 29 meters. So I come to my graph. Meters is on the y-axis. So let's see, I'm going to find 29. Here it is. Right there, in between 28 and 30 is 29. And it says to put a box. So I'm going to go over once right here. But if I look, he's going to be at 29 feet again, right there. So I should actually have 2 boxes because you're mentally kind of creating this invisible line, horizontal line, and he's going to be at a height of 29 feet once right here and again right there. So put a box where the diver would reach a height of 29 meters. We did that. This would be evaluating the function given y find x. So we were given a value for y. Sorry, I keep moving the box on you guys. We were given a value for y of 29, and we had to go find these two x values. So let's see, if I were to trace down, looking for what time this happened at, he was at a height of 29 feet once at 0.5 seconds, and then the second time at 1.5 seconds. So those would be our two x values. X equals 0.5 seconds, and x equals 1.5 seconds. Let me just go double check those two numbers. Yep, 0.5 and 1.5. Last but not least, put a triangle where the diver begins. Put a triangle where the diver begins. The triangle is going to go right here. That's where the diver begins. We know that's where it begins because if I look, what time is this? X-axis is seconds, so this would be at 0 seconds, meaning no time has gone by. That's how we know this is where he is starting. So on the graph, look at this graph as a whole, what ordered pair would that be? Well, if it's on the y-axis, that would be the y-intercept. So this would be finding the y-intercept. What is that ordered pair? Let's go look. 0, comma, right in between 24 and 26, that's 25. So that's 0, comma, 25. What does that ordered pair mean if I were to write it with my labels? Well, x is seconds, so 0 seconds. And then what was y about again? If you forget, go look at the y-axis. Height in meters. Oops, so I think I've been using feet this whole time. Sorry about that. That means that this should be meters. I'm just going to go back and fix that. I'm so used to writing feet instead of meters. My bad. Easy fix. So 0 meters. This shouldn't be feet. This should be 30 meters. Alright, there we go. So coming down here, 0 seconds, 25 meters. And just to emphasize, 0 seconds, no time has gone by. So that means that this is the starting height. 0 seconds means no time has gone by yet. No time's gone by yet, so the starting height is 25 meters. Now that we have a really nice visual start to how real-world questions are going to work moving forward, let's get into this awesome real-world question that deals with Danny McCaskill's ride, and it's in Spain. This is a screenshot, like a slow motion time lapse of his fall into the ocean at the end of his ride. And if we look at the shape it makes, if I were to follow this path, what shape does that look like? Well, I'm hoping from the sketches we've been doing, it kind of looks like a part of this. And what is this called? Starts with a P. That is called a parabola. And because it makes a parabola, let's answer this first question. Welcome to Gran Canaria, a small island off the coast of Spain. What shape of the graph would model it? Well, I kind of gave that one away, sorry. Parabola. Parabola just means that U shape. That's how many of us are used to calling it. So what are parabolas connected to? What function? So if you look at your table from day one, the general equation of a parabola is a quadratic function, which is f of x equals, I'm going to start it off and we'll see if you can finish it. Ax squared is how it starts. Can you finish it? I'm hoping next that we are going to write ax squared plus bx plus c. That's my general quadratic function equation. Now it says, does he complete the full shape of this function? And do you think this will have an effect on our use of the parent function formula? So if you noticed, I was able to draw this as a solid line, but this was kind of like a dotted imaginary piece. So does he complete the full shape if it's only kind of like half of it right here? The answer would be no. Only completes part of the, and I'm going to make the full shape, but he only does a part of it, right? So if I kind of make this match, he only does like that much of it. And the rest of this he didn't do, because he started here and ended up over here. We have our first official real-world model of the unit, and it's going to be the falling objects model. We'll see how this connects to his fall into the ocean in just a second. If you have a highlighter, go ahead and highlight this. So we're going to learn what model we can use to model his fall. It's going to be f of t equals negative 16t squared plus h naught. So you might have just thinking, like, man, what did she just say about that? So h with this little 0 in the subscript location is called h naught. I'm going to write it over here. Why it's called h naught, I don't know, but it is, so we are going to get used to using that vocab. I should look that up because every year people ask, and it's a great question. But that little 0 subscript, we'll talk about what it means in a second. But again, it's called h naught. Let's get to defining our variables. So h of t, I should have used h instead of f to be consistent. H of t equals. H of t is the height, so that's why it's good to use h. H for height at any time during the fall. Height at any time during the fall. H naught, or h with this little 0 subscript, always represents the initial height. So you can almost think of it as this little 0 telling you that no time has gone by. This is where you're starting. It's our initial height, our starting height. And then t is my time. Now that we have this model to work with, let's read this first question. It says, welcome to Gran Canaria, a small island in the Atlantic. GoPro athlete Danny McCaskill is finishing his ride with a fall into the ocean. The ramp he is riding off of is approximately 75 feet above the ocean. How long until he hits the water? Let's first define our variables. So we'll have t and h of t. So t, as we know from what we just wrote above, is time. And here, it doesn't give me a measure of time in this question, but if we're being reasonable in terms of modeling that fall into the ocean, it definitely didn't take hours, definitely didn't take minutes. That we would measure in seconds. So we're going to let t be time in seconds. And h of t, as written above, is going to be height. I'll just write height, but we'll know that we're talking about his height at any time during this path into the ocean. So now let's talk about how to build this model. The general model, remember how in Unit 5 we always wrote our general model? Highly recommend it here too. So h of t equals negative 16t squared plus h naught. Now to complete this model, this doesn't change. This always stays the same. This negative 16 actually comes from or deals with a physics connection to gravity on Earth. So for as long as we're dealing with questions on Earth, this negative 16 will never change. If we change the planet, then that number will change. And we actually will be looking at some examples on different planets later on. But for as long as we're on Earth, that number never ever changes. So really, the only thing we need a value for is this guy right here. And if we look above, h naught is the initial height. Are we told something about the initial height? Go ahead and read. Let's see, it says the ramp he's riding off of is approximately 75 feet above the ocean. So if I look at this picture here, we're saying if this is the water, right, if I kind of trace over the water line, this ramp that he's jumping off of, the distance from here to here is 75 feet. So his starting height is 75. I can fill that in. H of t equals negative 16t squared plus 75. There's my model. Now the follow-up question is still something we need to answer. We have our model, which is great. We're going to use it. It says, how long until he hits the water? So we have to ask ourselves, where's the water? Well, the water is 0 feet off of the ground. So water equals 0. But where are we going to put that 0? So if we look at how we defined our variables, it's definitely not going to be time. We already established what his starting height was. This question is not changing the starting height. This is where he ends up. We are given a value now for his height at any time during the fall. So we're asking, well, when is his height equal to 0? That's what this question is asking. And h of t represents that current height. So we are actually going to set this model equal to 0. So we have let h of t be 0. And from here, we'll be using our skills that we've been practicing to solve by square roots. I have no middle term. See how there's no plus 8t or minus 6t in the middle? So I can solve by square roots. Remember from our prior knowledge learning these past couple days, our first step will be to isolate this t squared. So I'm only looking at the right side. I'm going to ask myself, is there something I could add or subtract? Well, I see this positive 75. I can subtract that from both sides. So I get negative 75 equals negative 16t squared. And then I remember that negative 16t squared means negative 16 times t squared. So we'll divide both sides by negative 16. We get t squared equals, let's get our calculators out. You get yours out, I'm going to get mine out. So we can do this math together. Negative 75 divided by negative 16. And when I typed that into my calculator, I got 4.688. I'm going to round to 3 decimal places. The calculator actually told me 4.6875, but I'm looking to round it to the 3rd decimal place. So I'm looking to round it to this spot right here. When I look at the 5 or more, it's going to change that 7, and we're going to go up to 8. Are we done? I'm trying to solve for t. Well, let's see, t squared. So now that we have successfully isolated t squared, what undoes squaring? The inverse operation for squaring is square rooting. So we're going to take the square root of both sides. Remember, in your calculators, you're going to hit the second button first, and then you'll hit x squared, because above x squared, for most of your calculators, it looks like a purple square root sign. We're trying to get to that square root sign, and this button on your calculator is purple. So we use the second button to get to any function that looks purple. So hit second x squared, and it should create a square root symbol on your calculator. And then we can type in 4.688 and hit enter. And we get t equals 2.165, rounding to 3 decimal places. And t is time. We measured time in seconds. So seconds is our label. So this means it will take him 2.165 seconds to hit the water. Notice I did not put a plus or minus. What I mean is I didn't do this. And the reason I did not put it there, so I'm going to take it away, is that now that we're in the real world and we're dealing with time, we can't have negative time. So mathematically we do get a plus minus answer, but for my real world answer, I'm only going to keep the positive. This concludes our flipped notes for tonight on our start of real world applications. If you would like to start taking a look at the next question, please do so in pencil. That way we can adjust as needed. But that would be great if you start taking a look at the next one. Have a great day, everybody. Any questions, please send me a reminder. Bye.